Welcome to Week 5 summary of the course Fundamentals of Electronic Materials and Devices. In this week, we will continue our discussion on p-n junction. We saw earlier that a p-n junction at equilibrium, the Fermi level tends to line up. There is a depletion region that is created at the interface. The depletion region exists in both the p side and the n side, and the width of the depletion region is inversely proportional to the concentration of the dopants. Now we have to see what happens when we apply a bias to our p-n junction. The bias can either be forward bias or reverse bias. In the case of forward bias, we connect the p side to a positive terminal and the n side to the negative terminal. In this case, the external potential is opposite in direction to the built-in potential. So the net potential at the junction decreases and the Fermi levels are no longer aligned. So instead of V0, we have V0 minus V external, where V external is the external potential. We can look at this in terms of carrier injection. So the P side, as I said, is connected to the positive terminal, which means we have holes that are injected into the P side of the p-n junction. These holes then cross over through the depletion region and then move on to the n side where there are minority carriers. Similarly, electrons are injected on the n side, and these electrons cross over the depletion region and move on to the p side where they are minority carriers. Thus, current in a p-n junction in forward bias is due to the injection of the minority carriers. These are electrons in the p side and holes in the n side. So we can look at minority carrier injection. Now this happens because in forward bias, the barrier is lowered, which means as V external increases, the overall barrier decreases, and I have more number of minority carriers that are injected into my p-n junction. Now these being minority carriers will tend to recombine with the majority carriers and will finally get annihilated. We can define average diffusion length LE, where LE is nothing but square root of a diffusion term dE times tau E. Tau here refers to the minority carrier lifetime, and dE, which is the diffusion coefficient for electrons on the p side, depends upon the mobility mu E as kT mu E by E. So LE and dE, which corresponds to electrons, happens on the p side because remember we're talking about minority carriers, and similarly LH and DH, which refer to the holes, happens on the n side. So we can then define a total current in the case of forward bias. The total current is nothing but the sum of the contribution from the electrons and the holes, and we can write the total current J as the product of some Js0, where Js0 is called the reverse saturation current, times a term which depends upon the external potential. So the current J in the forward bias direction of a p-n junction increases exponentially with the applied external potential. Js0 is called the reverse saturation current, and it depends upon the dopant concentration, the diffusion length, and also the diffusion coefficients. So for a given p-n junction, at some temperature, Js0 is a constant. Now, what happens when we connect a p-n junction under reverse bias? So in this case, the p side is connected to negative, n side is connected to positive, so it is the opposite of forward bias. So now we have an external potential that is in the same direction as the built-in potential. So the barrier actually goes up. So the current under reverse bias is very small. We have thermally generated electron-hole pairs in the depletion region, and because of the potential, these thermally generated carriers will get separated, and they constitute a small dark current, which is nothing but the drift current, and this is equal to Js0. So a PN junction essentially acts as a rectifier. In forward bias, we have an exponentially increasing current, while in reverse bias, we have a very small drift current. We can also look at what happens to the depletion region. So W0 is the width of the depletion region under equilibrium. When we apply a forward bias, we are pumping in carriers into this depletion region, and we are reducing the barrier, which means the overall depletion width decreases, and this decrease is proportional to square root of V0 minus V external by V0. Consequently, when we apply a reverse bias, we are actually pulling away carriers from the depletion region, which means the overall width increases, and the increase in width is proportional to square root of V0 plus V external divided by V0. Now, if we keep on increasing the voltage in reverse bias, we basically have a breakdown of the junction, which means there is a really large increase in current for a short voltage increase. There are two breakdown mechanisms that are operative. When we have low dopant concentration, we have what is called an avalanche breakdown. This is because when the dopant concentration is lower, the depletion width is very large, and so the electric field that is applied causes the carriers to ionize. These ionized carriers, when they hit another atom, can release even more carriers. So carriers are either electrons or holes. So we have a large increase in current due to impact ionization. So this is the mechanism in avalanche breakdown. On the other hand, if we have a high dopant concentration, the width of the depletion region is small, in which case we basically have tunneling of the carriers through the depletion region, and this is called Zener breakdown. So far we have seen PN junctions where both P and the N regions are made of the same material. We call these homojunctions. We also can have PN junctions where the P and N materials are actually different. These are called heterojunctions, and there are different ways in which heterojunctions can be grown, but normally we need a layered by layered growth. There are other growth modes also available called Volmer-Weber, which is an island growth mode, or Stransky-Krasnov, which is a layer plus an island growth mode. But for heterojunction, we need what is called a Frank-Van der Merwe method, or a layer by layer growth. Here the band alignment is slightly more complicated because the conduction bands and the valence band do not align even when the junction is not formed. So remember, in the case of a homojunction, both EC and EV were the same before the formation of the junction. So here EC and EV are different because they are different materials. This leads to added states that are created at the interface when junctions are formed, which means by properly choosing the heterostructure materials, we can greatly increase the carrier transport across the junction. Heterostructures are especially useful when we come to optoelectronic devices. With this, we will conclude the summary of week 5. In both week 4 and week 5, we focused mainly on junctions formed from two materials. Next, we will look in week 6 at what happens if we have two of these junctions come together. That is, we will look at transistors. Thank you.